morning everyone. So today we will start with the continuation of the embedded systems. So where in the previous class we discussed about what is an embedded system and what are the examples for embedded system and how an embedded system is different from a general computing system. And now we shall discuss what are the elements of an embedded system. So with respect to elements of an embedded system, so we have the main core. So where core represents the heart of any embedded system. So with respect to the core, so we have what we call as input, I/O ports, or we call them as the sensors. Then we have the output ports, or we call them as the output, which is nothing but actuators. And along with this, so we require a storage unit. So where I can call this as my memory. So to this memory device, so we can also connect what we call as the communication interface. Communication interfaces. Okay. So now as you can see, so these are nothing but the elements of an embedded system. So now for every system or for an embedded system to perform its operation, so we require what we call as the input device, or we call them as the input ports. Okay. So now we add for every embedded system, so it has to sense something. So that is from the surrounding environment or to what type of application it is being used. So for your input, so we have what we call as sensors. So where sensors are the one which act as an input device to my embedded system. So where at the input end, so we have what we call as keyboards, switches, then buttons, so these are all which constitutes any input to a embedded system. That means with the help of a switch we can turn on or off the light. Okay. Similarly, where keypad, where we are going to input something. So that's why here, so these are all forms the input of any embedded system. So now, so we are going to sense that input with the help of sensors, where sensors are the one which act or which are connected at the input end of your embedded system, or which is going to be used as a sensing element within the surrounding environment or to what type of application we have used. Then we have what we call as the core of the embedded system. So where with respect to the core of the embedded system, so we can have microcontroller, microprocessor, or we can have a CISC or FPGA or a DSP, that is digital signal processor. So the core can be made with respect to any one of this. So that is what type of application you are going to use. Depending upon that type of application, you can choose the core to be a controller, a processor, or application specific, or it is field programmable gate array, or it is digital signal processor. So now whatever you have sensed, so that will be given as an input to your core of the embedded system. So once it is been sensed, so it is going to perform, it is going to process, then after processing it is going to produce the output. So now at the output end, so output are also called as the actuators, where actuators are the one which is going to perform the action depending upon the input what it has been sensed from the sensor. So where actuators are like LED devices or buzzers or some motors, so this forms the output of your embedded system. So that means whatever it has been sensed, for example, if we have used a fire sensor, so then it is going to sense the fire and then it will be indicated on what type of device we have connected at the output end. If suppose if an LED is connected, the LED will turn on, or if it is a buzzer which has been connected, then the buzzer will turn on, or if a motor is been connected, so it is going to rotate. So that means, so depending upon what type of application, so we can indicate the action of the input with the help of these actuators. Then we have what we call as memory. So memory, as we know, so if you want to perform this action of an embedded system, so now the program has to be stored in a device. So that we are going to do with the help of a memory unit, where the memory can be any one of this, either you can go for a ROM or a RAM. So where depending upon your ROM, so you have UV ROM, then we have programmable read-only memory, then we have OTP, that is one-time programmable, then we have EPROM, then we have E2 PROM and etc. Then we have flash memory. So that is depending upon what type of application your embedded system has been designed. So you can choose any one of these type of ROM depending upon whether you require a volatile or a non-volatile memory. So now with respect to your RAM also we have SRAM as well as DRAM. That is static RAM and dynamic RAM. So where it is random access memory, it is RAM, and your ROM is read-only memory. That means whatever the program part you are doing, that means your software part, so that will be completely hidden inside this memory, and the type of memory can be any one of these two. So other than this, what are the other elements which we require with respect to our embedded system is like other communication interfaces. For example, your USB device or your RS-232, that means if you want to have a parallel or if you want to have a serial communication interface, so those communication interfaces can also be attached to the core of your embedded system. So other than this, so communication interfaces can be any other USB cable, so which is used for transferring of information from the source to the destination. So these all blocks what we have represented here, this forms the elements of your embedded system. So now as I told, the main important thing here is with respect to the core. So the core can be any one of these as I already mentioned. So now we were discussing about the core of the embedded system. So where if we consider the microcontroller. So as we know that microcontroller, we have from 4-bit to 64-bit. So now what is the speciality of this microcontroller? Where microcontroller is a system on chip, it is SoC. So where all the components are embedded inside a single chip. That means to say that, so where it is a CPU, central processing unit. So where along with the central processing unit, it consists of input, output, then timer, then serial interfaces, then counters. So all these are embedded inside a single chip. So that is your microcontroller. So where in most of the applications we go for microcontroller because the complexity involved with respect to using or doing any application with respect to microcontroller is very easy because all the devices are inbuilt with respect to a single chip. So next we have the microprocessor, so which is also the core of your embedded system. So microprocessor is the one which has a central processing unit. So where along with the central processing unit, so the other devices like your memory, then your timers, then other serial interfaces. So these all devices are not inbuilt. So we need to connect externally. That means here, so we have only the processing unit. So to this processing unit, so we need to connect all these devices additionally to your microprocessor. So where the complexity involved in designing a microprocessor is more when compared with respect to your microcontroller. So next core what we have is an application specific, or so that is a SIC, so which is called as application specific integrated circuit. That means, so where it is designed for a specific application. So for what type of application we need our core, so we can design. For example, if we want it to perform only the washing operation, so then we are designing our embedded system only for a specific application. Similarly, we have FPGA, that is field programmable gate array. So where we are going to program our device, that means you are going to write the instructions and we need to program. So depending upon the programming of our device, so it is going to perform its operation. So next we have DSP, that is digital signal processor. That means for processing of the signal. So for signal processing applications like voice processing, video, audio. So for these applications we are going for this digital signal processor. So then we have one more type of processor which is called as general purpose processor. That is, the core is also general purpose. So that means, so we can use only for a general purpose. That means we are not designed our core for performing a specific application, where we can also design our core of the embedded system for performing numerous operations. So this is about the core of the embedded system. So along with this, so we have other integrated circuits and subsystems. That means other than your controller, processor, SIC or DSP, so we can also integrate other ICs if suppose if its operation cannot be controlled by using only a controller. So then additionally we can also go for a microprocessor or a DSP with respect to your core. So this complete thing forms the elements of an embedded system. The next topic is related to the differences with respect to a microprocessor as well as a microcontroller. So as I already was discussing with respect to the elements of an embedded system, I told, so what is a microcontroller as well as what is a microprocessor. So now here we will just list what are the differences we have with respect to choosing an core, whether I can have to choose a controller or I have to go for a microprocessor. So the very first important thing is I can say that microcontroller is a system on chip. Okay, that means to say all the elements are embedded inside a single chip. So coming to the microprocessor, so it has only a CPU. So where along with the CPU all other hardware devices are to be interfaced. Then second one is complexity in designing. In designing a microcontroller is easy, or I can say that it is not complex, but in case of a microprocessor, complexity in designing is more. Then the third one is it is going to consume less power. So how it is going to consume less power means, so here all the devices like your timer, your counter, your memory, your input, output, so everything is being embedded. So that's why, so if you just pass a 5 volts, so it is going to supply power to all the devices. So but in case of microprocessor, So consumption of power is more because all the devices are connected externally. So that's why you have to that's why here, so you have to give separate power supply to each individual devices. So that's why the consumption of power is more in the case of microprocessor. And also here in case of microcontroller, so additional memory. So memory can be interfaced externally So here in the case of microprocessor, memory can be interfaced externally. So in both of them the memory can be interfaced externally, but in case of microcontroller, so we have more number of registers, so that's why external memory requirement is not required, but in some cases so we might need external memory. In case of microprocessor, we have few registers for storing of your data as well as for movement of the data. Next is here in case of microcontroller, we have few addressing modes. So addressing modes are nothing but the way in which we can access the data or the way in which it helps in movement of data from memory to register or from register to register or from register to memory. So now in the case of microprocessor, so we have more number of addressing modes. So that's why here, since we have more number of addressing modes, so the complexity is more in the case of microprocessor. So these are some of the common differences what we have with respect to a microcontroller as well as a microprocessor. So after knowing the differences with respect to a microprocessor and a microcontroller, so the next important thing what we need to know with respect to selection of an embedded system is what type of processor we require. So whether you require a RISC processor or a CISC processor. Where RISC stands for reduced instruction set computing, and CISC stands for complex instruction set computing. So complex instruction set computing in the sense, so it will be having more number of instructions. So since it has more number of instructions, so it will be very difficult for us to remember how many number of instructions are there. So the very first differences is depending upon the instructions. So in case of RISC we have less number of instructions. Then the second is the addressing modes. So in the case of CISC we have 8 to 10 addressing modes. So I told what do you mean by addressing modes when I was explaining about the differences with respect to processor and a controller. So addressing modes are nothing but the way in which you can access the data to register and memory, or from memory to register. So here it has only few addressing modes. So few addressing modes in the sense it can have only 5 for example. Then the third is, so the size of the CISC instruction. So it is variable. Variable instruction size, but in case of RISC it is fixed instruction size. So size in the sense it can be 8-bit or 16-bit. So next is the complexity. So since it is CISC, as the name itself is indicating, so it is complex. So it consists of complex instructions. So it consists of simple instructions. So that means you can easily understand the instructions. So next is, in case of your CISC, so we give the complexity lies with respect to hardware. In the case of RISC, the complexity lies with respect to the software. Next, in case of CISC, so here we used transistors to store complex instructions. In case of RISC, transistors are used as memory. That means they are used to store the data. So in case of CISC, since the complexity lies with respect to the hardware, so the designing of the hardware is complex, and in the case of RISC, since the complexity lies with respect to the software, so the complexity lies with respect to the compilation of the program. So where in the case of CISC, so since it has complex instructions, so it requires multiple clock cycles. So clock cycle in the sense, so in case of processing of an instruction, it can take 3 clock cycle or 4 clock cycle, where in each clock cycle, so we have a fetch state, then decode as well as execute. So in order to complete these 3 set of operations, so it might take multiple clock cycle depending upon how many number of bytes an instruction is. So in the case of RISC, so it consists of few clock cycles for processing of the instruction. So these are some of the differences what we have with respect to RISC as well as the CISC. So next we have classification of embedded system. So where in the classification of embedded system, so we are going to classify embedded system on 4 categories. So first is based on complexity, then we have based on generation, then third one is based on deterministic behavior, then fourth one is based on triggering. So now we will discuss one by one. So now based on complexity, so based on this, so we have what we call as small scale, then we have medium scale, and third one is large scale. So now here with respect to small scale embedded system, that is, so it is simple design, and it requires 8-bit or 16-bit microprocessor or microcontroller for designing, and also it has simple hardware and software. Example, the electric toys or battery operated. So the next is medium scale, so where it has bit medium complexity in hardware and software designing, and it consists of 16 bits slash 32-bit microprocessor or microcontroller. So here example is industrial machines, next is large scale, where we have more complexity involved in designing of hardware and software, and it is 64-bit to 32-bit microprocessor or microcontroller, and for example your smartphones, this 5G generation. Okay. So this is with respect to the based on complexity and performance wise. So performance in the sense, so whether the time should be critical or not. So here the performance with respect to small scale, so it's not too much critical. So here it is critical. In the case of large scale, it is deterministic. That means it has to meet its performance, or the time is very critical and it should perform its operation in real time. So next is based on generation. So we have 4 generations and additionally a 5th generation, which is the present generation. So what the technology we are using at present is of 5G. So where in the case of first generation, so it has 8-bit slash 8-bit microprocessor and 8-bit microcontroller, and it is used for simple applications. As I mentioned, in small scale. So we are using this first generation with respect to smaller applications like your keypad phones. Next is second generation. So where in the case of second generation, so we have 16-bit microprocessor and 8-bit microcontroller. So where we have higher end applications with respect to second generation. So since we have 16-bit microprocessor, the complexity is more with respect to designing the circuits with respect to 16-bit microprocessor. So example is the SCADA systems. Next comes the third generation. So where in the case of third generation, so we have 32-bit microprocessor and 8-bit microcontroller. Sorry, it is 16-bit microcontroller. So where as the size of the bits with respect to processor and controller is being increased, so the complexity involved in designing the circuit also has been increased here. So where in the third generation we can go for, example for this is we can use it for processing application, that is digital signal processing applications. Where in the fourth generation, so we have 64-bit microprocessor and 32-bit microcontroller. So as the size of the processor is being increased, so we can use it for designing of system on chip circuits. So for example, your smartphones, then coming to the fifth generation, where it is more than this, more than 64-bit, that means it is 128-bit, okay, and the present iPhones and your laptops, so whatever we are using, so those at present it is of fifth generation. So next we have the classification based on deterministic behavior. So deterministic behavior means whether it is performing its action in real time or not. So where in deterministic behavior we have hard real time and soft real time. So in the case of hard real time, it need not be deterministic. Need not be deterministic. But in the case of soft real time, it need to be deterministic. That means to say that it has to meet its deadline. That means if we have specified some deadline, it has to perform its action within the specified time interval. In the case of soft real time, so it has to meet its deadline here without missing. So in case of hard real time, it can miss the deadline, but in case of soft real time, it is not going to meet it is not going to miss the deadline. If any deadlines are missed here, some event is going to happen. That is depending upon the triggering. That is the last classification, that is based on triggering. That means if it is not going to meet the deadline, it is going to cause some actions or some event will occur. So that means if we have fixed a time to explode a bomb, so then if it meets the deadline, it is going to explode the bomb. After the bomb gets exploded, so we know that some disaster will happen. So that means some event will happen depending upon the triggering action. So that's why in the case of hard real time, if it that means to say that there are chances that it can miss the deadline. In case of soft real time, it is not going to meet the deadline and it is going to perform some event or action when some triggering event will happen in the case of real time. So these are the 4 different classifications of the embedded system. It is depending upon complexity and performance. So we have small scale, medium scale and large scale, and depending upon the generations, we have 5 generations, and based on deterministic behavior we have classified into 2, that is hard real time and soft real time, and it is based on triggering. So that means based on triggering in the sense, so some event will happen if it meets the deadline or if it doesn't meet the deadline. So after knowing the classifications of embedded system, so now we should know what are the different application areas in which embedded systems are used. Application areas of embedded systems. So as we all know that the household appliances, it is in case of mixer grinder, so your TV, etc. It is nothing but consumer electronics. Then we have automation. In automation, that is providing security to your home automation system. So that is with respect to your automation, as well as in automotive industry, in automotive electronics, that is in your car, we have ABS anti-braking systems. Then opening of then in case of aerospace, then we have in case of industry, then military applications, then in banks, so these are few applications what I have listed. So with respect to your embedded systems, so we have plenty of applications with respect to your embedded system. Thank you.